There are planets in the universe that are hotter than stars. For most of human history, stars defined the upper limit of heat and energy. They represented the most intense environments known to exist. Planets, by contrast, were understood as secondary objects, cooler, passive, and fundamentally different. That distinction appeared stable. It felt complete, but it was never tested beyond a single example. And now, it no longer holds. The discovery of ultra-hot exoplanets, worlds such as KELT 9b, has forced a revision not only of planetary science, but of the way physical categories are defined. This is a planet with an atmosphere heated to thousands of degrees. At these temperatures, molecules cannot remain intact. Chemical bonds break apart into atomic components. Elements such as iron exist not as solids or liquids, but as vapor distributed across the atmosphere. These conditions resemble stellar environments more than traditional planetary ones. The contradiction is not subtle. A planet, by definition, was not expected to exceed the thermal intensity of many stars. Yet this object does. It exists within a range that was previously assigned to an entirely different class of astronomical bodies. This forces a structural reconsideration. The categories themselves are not absolute. They are descriptive approximations, useful but limited. From this point, a broader conclusion begins to emerge. The universe does not organize itself according to human definitions. It operates across a continuous spectrum of physical states. The distinction between planet and star is not a fixed boundary. It is a range shaped by mass, energy, and interaction. Once this boundary begins to dissolve, a deeper realization follows. The more we observe the universe, the less it resembles a collection of familiar objects. Instead, it reveals a system of processes, dynamic, variable, and often counterintuitive. This shift is gradual but irreversible. It changes the question being asked. The focus is no longer on identifying what a planet is. It becomes an attempt to understand how far planetary conditions can extend. This video explores that range, not as a list of unusual discoveries, and not as a sequence of isolated facts, but as a structured examination of what these worlds reveal about underlying reality, about the limits of physics, about how planetary systems form and evolve, about the conditions under which life might exist, and about the position of Earth within a much larger and more complex structure. Each of these topics emerges from the same source: observation. Because extreme planets are not anomalies in the traditional sense. They are not errors. They are not exceptions to otherwise stable rules. They are outcomes, natural results produced by the same physical laws that shape all systems. This leads to a critical shift in interpretation. The universe is not built around stability as a default condition. Stability exists, but it is only one possible outcome among many. Under different initial conditions, the same laws produce entirely different environments. Some of those environments appear familiar, many do not. At this point, it becomes necessary to reconsider the role of expectation in science. Expectation is often based on limited data. When the sample size is small, patterns appear stronger than they are. The solar system provided the first and only reference for planetary structure for centuries. From that reference, a general model was constructed. It was coherent, it was predictive, but it was incomplete. As new data became available, that model began to expand, then adjust, and eventually fragment into multiple possibilities. This process did not invalidate the original model. It placed it within a larger context. The solar system is not a universal template. It is one configuration within a broader distribution. This realization changes how new discoveries are interpreted. A planet with extreme temperature is no longer seen as a violation of rules. It is understood as an extension of those rules into a different region of parameter space. A system with unusual orbital dynamics is not treated as unstable by default. It is examined as a result of different initial conditions and interactions. In each case, the emphasis shifts from anomaly to explanation, from surprise to structure. There is also a methodological implication. Observation is selective. Current detection methods favor certain types of planets, larger ones closer to their stars, objects that produce measurable signals. This introduces bias into the data. Many planetary systems likely remain undetected, not because they are rare, but because they are difficult to observe with existing instruments. This means that the diversity already identified is not the full picture. It is an early approximation. Even so, the variation that has been observed is sufficient to support a broader conclusion. Planetary systems are not uniform. They are outcomes of a continuous and highly variable process. From this perspective, the initial paradox becomes easier to place. Planets hotter than stars are not contradictions. They are data points. They mark one region within a much larger spectrum of possible conditions. And once that spectrum is acknowledged, a different type of question emerges. Not whether such worlds should exist, but how many others exist beyond current detection. There is no immediate answer to that question, but the direction is clear. Each improvement in observational technology expands the known range of planetary conditions. Each new dataset refines the structure of what is considered possible. Understanding does not converge toward simplicity. It expands toward complexity with increasing precision. This is the starting point of the exploration, not a catalogue of extreme worlds, but an investigation into what those worlds represent. They are not just distant objects. They are evidence. Evidence that the universe operates across a broader range than intuition suggests. Evidence that classification systems are approximations, not boundaries. Evidence that reality extends beyond familiar structure. And to understand how this realization emerged, it is necessary to step back, to examine the assumptions that defined early planetary science, to understand why those assumptions appeared valid, and to trace the moment when observation began to challenge them. Only then does the full scale of this shift become clear. Before 1995, planetary science was built on a single reference point: the solar system. There were no confirmed planets orbiting other stars, no comparative data, no statistical distribution. Only one example of how a planetary system might form and evolve. From that single system, a framework was constructed. Rocky planets occupy the inner region, close to the star. Gas giants form farther away, beyond a certain distance. Orbits remain mostly circular and stable over long timescales. Temperature decreases gradually with distance from the central star. This structure appeared coherent. It explained the observed arrangement. It aligned with gravitational theory and early models of planetary formation. But it carried an unspoken assumption that this structure was not just one example, but a typical one. The limitation was not conceptual, it was observational. Detecting planets around other stars is extremely difficult. A star emits vast amounts of light, while a planet reflects only a small fraction of it. The difference in brightness can exceed a factor of 1 billion. At such contrast levels, direct imaging becomes nearly impossible with earlier instruments. Any planetary signal is overwhelmed by the star's radiation. This meant that for most of the 20th century, planets outside the solar system remained undetectable. Not because they did not exist, but because they could not be isolated from the light of their host stars. As a result, the absence of observed exoplanets was interpreted cautiously, but it still shaped expectations. Without alternative examples, the solar system became the default model. This created a form of observational bias, not through incorrect reasoning, but through incomplete data. Patterns identified within a single system were extended outward. The assumption was that similar processes would produce similar outcomes elsewhere. Planetary formation models reinforced this view. According to early theories, planets form from a rotating disk of gas and dust surrounding a young star. Within this disk, temperature plays a central role. Closer to the star, temperatures are higher. Only materials with high melting points, metals and silicates, can remain solid. These materials combine to form rocky planets. Farther from the star, temperatures drop. Volatile compounds such as water, methane and ammonia can condense into ice. These ices provide additional mass, allowing the formation of large cores that can accumulate thick, gaseous envelopes. This explains the presence of gas giants at greater distances. The model is internally consistent. It explains why the solar system is structured the way it is. But internal consistency is not the same as universal validity. Another assumption followed naturally. If planets form within a disk and evolve under gravitational influence, their orbits should remain relatively stable. Over time, collisions and interactions may occur, but the overall structure should settle into predictable configurations. This leads to nearly circular orbits aligned with the rotational plane of the star. Again, this matches the solar system, and again, it was treated as a general rule. Thermal structure also appeared predictable. Radiation from the star decreases with distance. As a result, planetary temperature should follow a gradient. Hot near the star, cold farther away. This relationship seemed straightforward. It provided a simple way to estimate planetary environments based on orbital distance alone. Taken together, these assumptions formed a complete picture. A typical planetary system would consist of small, rocky planets in close orbits, large gas giants in distant orbits, stable circular motion, a smooth temperature gradient from inner to outer regions. This model was not arbitrary. It was grounded in physics and supported by observation within the only system available. But it was also limited because it relied on absence. No contradictory systems had been observed. No alternative configurations had been confirmed. The model was not tested against diversity. It was inferred from silence. There is an important distinction here. Scientific models are often built from available data. When data is limited, models tend to appear more certain than they actually are. This is not a flaw in the method, it is a constraint of observation. In this case, the constraint was significant. Without the ability to detect exoplanets, there was no way to measure how common or rare the solar system's structure might be. No way to determine whether planetary migration occurs. No way to observe extreme orbital configurations. No way to identify environments outside the expected thermal range. Theoretical work explored some of these possibilities, but without observational confirmation, they remained speculative. There were attempts to detect exoplanets before 1995. Astronomers searched for subtle changes in starlight. They examined variations in stellar motion. They looked for indirect evidence of unseen companions. But the signals were weak. The instruments lacked the necessary precision. Many early claims were later revised or withdrawn. This reinforced caution. It also prolonged the reliance on the solar system as the primary model.
As a result,
planet science entered the late 20th century with a well-defined framework and a significant blind spot. The framework explained what was known. The blind spot concealed what was not yet observable. This combination created stability in theory, but also resistance to unexpected outcomes. Because when new data eventually appeared, it did not fit the model, not partially, but fundamentally. The key point is not that early assumptions were incorrect. They were reasonable given the data available at the time. The issue is that they were incomplete. They described one region of possibility, not the full range. And without additional data, there was no clear way to distinguish between the two. This is the context in which the first confirmed exoplanets were discovered. A field built on a single example, a model that appeared stable, a set of expectations that had never been tested against large-scale observation. When that test finally occurred, the results did not refine the model, they disrupted it. And from that disruption, a new understanding began to form. The first confirmed exoplanet orbiting a Sun-like star was not discovered by direct observation. It was detected through motion. More precisely, through a small and measurable change in the motion of a star. When a planet orbits a star, the star does not remain perfectly stationary. Both objects orbit a shared center of mass. Because the star is much more massive, its movement is small, but not zero. This movement produces a subtle shift, not in position, but in light. The method used to detect this shift is known as radial velocity. It measures how the light from a star changes as the star moves slightly toward or away from the observer. When the star moves toward the observer, its light shifts toward shorter wavelengths. When it moves away, the light shifts toward longer wavelengths. This is the Doppler effect. It is the same principle observed in sound, where a passing object changes pitch depending on its motion relative to the listener. In this case, the effect is applied to light instead of sound. The shift is extremely small. It cannot be seen directly. It must be measured through precise analysis of the star's spectrum, its distribution of light across different wavelengths. By tracking these changes over time, a pattern emerges, a periodic oscillation, a signal that repeats. From this signal, several properties can be inferred. The amplitude of the shift, the degree of motion, indicates the strength of the gravitational interaction. This provides an estimate of the planet's mass, or more precisely, its minimum mass. The period of the oscillation, the time it takes for the pattern to repeat, reveals how long the planet takes to complete one orbit. From this, the orbital distance can be calculated using established physical laws. These measurements do not produce an image of the planet. They produce data. But the data is sufficient to confirm existence. When the first such detection was announced in 1995, it marked a turning point. For the first time, a planet orbiting a Sun-like star had been confirmed through repeatable measurement. The system was real. The signal was consistent. The interpretation was supported by physics. It was the beginning of observational exoplanet science. But the result itself was not what had been expected. The detected planet did not resemble Earth. It did not resemble any planet in the solar system. Instead, it was a gas giant, comparable in mass to Jupiter, but located extremely close to its star. Its orbital period was only a few days. This implied a very small orbital distance, much closer than Mercury is to the Sun. According to the existing model, this configuration should not exist. Gas giants were expected to form in colder regions, far from the star, where volatile compounds could condense and accumulate. There was no mechanism in the standard model that allowed a gas giant to form so close to its star. And yet, the data was clear. The planet existed. This type of planet became known as a hot Jupiter. The name reflects both its size and its temperature. Large, gaseous, and exposed to intense radiation due to its proximity to the star. At first, this discovery was treated cautiously. It was possible that the system was unusual, an outlier, a rare case. But as detection methods improved, more examples were found. And then, more. Hot Jupiters began to appear in multiple systems, different stars, different regions of the sky, similar configurations. At that point, the interpretation changed. This was not an isolated anomaly, it was a recurring outcome, and that required an explanation. The solution came in the form of planetary migration. Planets do not necessarily remain in the positions where they form. During the early stages of a planetary system, interactions with the surrounding disk of gas and dust can cause large planets to move inward. Gravitational interactions with other planets can also alter orbits over time. These processes can shift a gas giant from a distant formation zone into a close orbit. This idea introduced a new level of dynamism into planetary science. Planetary systems were no longer static structures, they were evolving systems. Positions could change, orbits could shift, configurations could be reshaped. The implications extended beyond a single type of planet. If migration is possible, then the arrangement of a planetary system is not determined solely at formation. It is the result of ongoing interaction. This means that two systems formed under similar conditions can evolve into very different configurations. The radial velocity method continued to produce new detections. Each new signal added data. Each dataset expanded the known range of planetary masses and orbital distances. But it also introduced another important realization. The method itself has limitations. It is most sensitive to large planets in close orbits. These planets produce stronger gravitational effects and therefore larger, more detectable signals. Smaller planets, or planets farther from their stars, produce weaker signals that are more difficult to measure. This introduces a detection bias. The first planets discovered were not necessarily the most common. They were the easiest to detect. Even with this limitation, the impact was significant. The existence of hot Jupiters alone was enough to challenge the original model of planetary systems. It demonstrated that the solar system is not the only possible configuration, and it suggested that many others exist, shaped by processes not previously considered in detail. The detection revolution did not begin with a gradual refinement of theory. It began with a contradiction, a single observation that did not fit the existing framework. From that point, additional observations confirmed that the contradiction was not an exception. It was part of a broader pattern. This marks a shift in scientific process, from inference based on limited data to analysis grounded in observation, from assumption to measurement. And as the number of detected planets increased, the original model did not disappear. It became one case among many, a valid example, but no longer a universal template. This transition sets the stage for the next development, because once detection became reliable and once multiple systems could be observed, the question changed again. Not whether planets exist around other stars, but how different those planets can be, and how far those differences extend. The discovery of hot Jupiters did not simply add a new category of planets, it challenged the structure of planetary formation theory itself. According to classical models, gas giants should form beyond a specific boundary known as the frost line. This is the distance from a star where temperatures are low enough for volatile compounds, such as water, methane, and ammonia, to condense into solid ice. That detail is critical. Ice increases the amount of solid material available during formation. With more solid mass, planetary cores can grow larger. Once a core reaches sufficient size, it can rapidly accumulate gas from the surrounding disk, forming a gas giant. Inside the frost line, this process should not occur. Temperatures are too high. Volatile materials remain in gaseous form and cannot contribute to solid core growth. As a result, only smaller, rocky planets are expected to form in these inner regions. This distinction created a clear structural rule. Rocky planets close to the star, gas giants far away. Hot Jupiters violated that rule directly. They are gas giants located well inside the region where they should not be able to form. The contradiction is not minor. It affects the foundational assumption about where different types of planets can exist. There are two possible ways to resolve this contradiction. Either the formation model is incorrect, or the planets did not form where they are currently observed. The second option proved more consistent with the available data. This led to the introduction of a new mechanism, planetary migration. Planetary migration describes the movement of a planet from its original formation location to a different orbital position. This movement is not random. It is driven by interaction. In the early stages of a planetary system, a young star is surrounded by a dense disk of gas and dust. A forming planet interacts gravitationally with this disk. These interactions exchange angular momentum between the planet and the surrounding material. As a result, the planet's orbit can gradually shift. In many cases, this shift is inward. The process can be slow and continuous. Over time, a gas giant that formed beyond the frost line can move closer to the star, eventually settling into a tight orbit. This explains the existence of hot Jupiters without requiring a complete rejection of formation theory. But it introduces a new layer of complexity. Disk interaction is only one mechanism. Gravitational interactions between planets also play a significant role. In systems with multiple large planets, mutual gravitational influence can alter orbital paths. Close encounters between planets can transfer energy, changing both the shape and size of their orbits. In some cases, one planet moves inward while another is pushed outward. In more extreme cases, a planet can be ejected from the system entirely. There is also the effect of orbital resonance. When two planets orbit a star with periods that form a simple numerical ratio, their gravitational interactions become synchronized. This can create long-term stability under certain conditions, but it can also lead to instability. Small perturbations can accumulate over time, increasing orbital eccentricity and altering trajectories. In densely packed systems, this process can destabilize the entire configuration. These mechanisms share a common feature. They introduce change. Before these discoveries, planetary systems were often modeled as relatively stable after formation. Once planets settled into orbit, their positions were expected to remain largely unchanged over long timescales. Migration alters that assumption. It shows that planetary positions are not fixed outcomes. They are temporary states within an evolving system. This leads to a key principle. Planetary systems are dynamic. They change over time. Their structure is shaped not only by initial formation conditions, but by ongoing interactions between planets, disks, and stars. This principle has several implications. First, the current arrangement of a planetary system does not necessarily reflect its original structure. A planet observed close to its star may have formed much farther away. A system that appears stable now may have undergone significant rearrangement in the past. Second, diversity becomes expected. If planetary systems evolve through interaction, then small differences in initial conditions can lead to very different outcomes. Two systems with similar starting points can diverge over time. One may remain relatively stable. Another may experience large-scale migration, orbital disruption, or planetary ejection. Third, the concept of a typical planetary system becomes less meaningful. Instead of a single standard model, this sets the stage for the next development. Because once multiple systems are observed and once their variability is confirmed, a larger pattern begins to emerge. Not just individual differences, but statistical diversity across the galaxy. The early phase of exoplanet discovery was defined by individual detections. Each new planet added a data point. Each system introduced a new configuration, but the sample size remained limited. That changed with the launch of Kepler's Space Telescope. Kepler was designed with a different objective, not to find a few planets, but to measure how common planets are. Instead of observing many stars briefly, Kepler focused on a single region of the sky for an extended period. It monitored the brightness of more than 150,000 stars continuously, looking for small periodic decreases in light. This method is known as transit photometry. When a planet passes in front of its star, it blocks a small fraction of the star's light. The result is a temporary dip in brightness. If this dip repeats at regular intervals, it indicates the presence of an orbiting planet. The signal is subtle. For Earth-sized planets, the change in brightness can be less than 1%. But with continuous observation and precise instruments, these signals become detectable. The strength of this method lies in repetition. One transit suggests a possibility. Multiple transits confirm a pattern. From this pattern, key properties can be derived. The depth of the brightness dip indicates the planet's size relative to the star. The time between transits reveals the orbital period. Combined with stellar data, this allows estimation of orbital distance. Unlike radial velocity, which is more sensitive to mass, transit photometry provides information about planetary size. Together, these methods create a more complete picture. As Kepler collected data, the number of detected planets increased rapidly, not by tens, but by thousands. For the first time, planet science had access to a large sample. And with that sample, a different kind of analysis became possible: statistical analysis. The results were clear. Planets are extremely common. Most stars do not exist in isolation. They are accompanied by one or more planets. In many cases, multiple planets orbit the same star in complex arrangements. This was not a marginal conclusion, it was a dominant pattern. The second finding was equally important. Planetary systems show a high degree of diversity. Some systems contain tightly packed inner planets. Others include large planets in eccentric orbits. Some show clear evidence of migration and past instability. Many of these configurations differ significantly from the solar system. This leads to a direct implication. The solar system is not a universal template. It is one configuration among many. It follows a structure that is internally consistent, but not representative of all systems. This realization changes the framework of interpretation. Previously, the solar system was used as a baseline. Other systems were expected to resemble it with minor variations. After Kepler, that assumption is no longer valid. There is no single baseline. There is a distribution. Within this distribution, some systems may resemble the solar system. Others may differ in one parameter, orbital distance, planetary mass, or system architecture. Some differ in multiple parameters at once. The result is not a standard model with small deviations. It is a wide range of configurations produced by the same physical laws. This reframes the central question. The earlier question, what is normal, becomes less useful. Normal implies a central tendency, a dominant pattern that most systems follow. Kepler data does not support a single dominant structure. Instead, it reveals variation. The more appropriate question becomes, what is possible? This shift has practical consequences. In planetary science, models are no longer built around a single expected outcome. Instead, they must account for a range of outcomes. Formation theories must explain not only stable, widely spaced systems, but also compact systems with multiple close-in planets. Migration models must account for both moderate shifts and extreme inward movement. Stability analysis must consider systems that remain unchanged for billions of years, as well as systems that undergo significant rearrangement. There is also a methodological impact. With large datasets, patterns can be identified more reliably. Frequency distributions can be measured. Correlations between planetary properties can be analyzed. Outliers can be distinguished from common cases. This allows for a more precise understanding of planetary populations. At the same time, limitations remain. The transit method is biased toward planets that pass directly between their star and the observer. If the orbital alignment is slightly different, the transit does not occur from our point of view, and the planet remains undetected. This means that even large datasets are incomplete. They represent a subset of all existing systems. Despite this limitation, the statistical conclusion is robust. Planets are not rare. They are a common outcome of star formation. This has a broader implication. If planetary systems are common, then environments capable of supporting different physical conditions are also common. Some of those environments may resemble Earth, many will not, but the range itself is significant. The Kepler era marks a transition from discovery to distribution, from individual examples to population-level understanding. And with that transition, the original assumptions about planetary systems are fully replaced, not discarded, but repositioned. The solar system becomes one data point, a well-studied example, but not a defining standard. This completes the shift that began with the first detection of a hot Jupiter. Initial contradiction led to new mechanisms. New mechanisms led to broader observation. Broader observation led to statistical reality. From this point forward, planetary science no longer asks whether unusual systems exist, it assumes they do. The focus shifts to understanding how they form, how they evolve, and how frequently they occur. And this opens the next stage of exploration. Because once the range of planetary systems is established, the attention turns to the details within that range, to the environments, to the physics operating under extreme conditions, to the limits of what a planet can become. Some planets do not warm gradually as they move closer to their stars. They cross a threshold, and beyond that threshold, the behavior of matter changes. On Earth, temperature defines environment. It separates solid from liquid, liquid from gas. It shapes weather, geology, and chemistry. But there is an upper range to those familiar transitions. Beyond a certain point, the distinction between these states begins to lose meaning. Ultra-hot exoplanets exist in that range. A clear example is Kelt 9b. This planet orbits extremely close to its host star. Its orbital period is less than 2 days. The distance is so small that the amount of incoming radiation is intense and continuous. Surface and atmospheric temperatures exceed 4,000 degrees Celsius. At this level, the environment no longer resembles a conventional planetary atmosphere. It begins to resemble a radiative system. The first effect is molecular breakdown. Under normal conditions, atoms combine into molecules, stable structures held together by chemical bonds. At extreme temperatures, those bonds cannot hold. Energy input becomes sufficient to separate molecules into individual atoms. Hydrogen molecules split into atomic hydrogen. Water vapor cannot remain intact. Complex compounds cease to exist as stable units. The atmosphere becomes a mixture of atomic components rather than molecular gases. This changes the chemistry. Reactions do not proceed toward equilibrium. Instead, they occur continuously, driven by temperature gradients. On the day side, molecules dissociate. As material moves toward cooler regions, atoms recombine. Then, as circulation returns that material to hotter regions, the process repeats. There is no stable endpoint, only cycles. The second effect is atmospheric escape. At high temperatures, particles move faster. For light elements such as hydrogen, thermal velocity can approach escape velocity. When that happens, atoms are no longer bound to the planet. They drift outward, forming extended clouds of gas around the system. Over time, this leads to gradual loss of atmospheric mass. The planet is not only heated, it is being altered. The third effect involves heavier elements. On Earth, metals exist as solids or liquids. On ultra-hot planets, that is no longer the case. Temperatures exceed the vaporization point of many metals. Iron, titanium, and other elements transition into gaseous form. They do not condense into surfaces, they remain suspended within the atmosphere. Spectroscopic observations confirm this. When light passes through or reflects off the atmosphere, it carries information about the elements present. Absorption lines reveal signatures of ionized metals. These are not theoretical predictions, they are measured signals. This leads to a structural change. The atmosphere is no longer defined by layers of stable gases. It becomes a stratified system where composition varies with temperature, altitude, and radiation exposure. Ionized regions form at higher temperatures. Recombined species appear in relatively cooler zones. But these layers are not fixed. They shift continuously. Tidal locking reinforces this instability. The same side of the planet always faces the star. Energy input is constant over one hemisphere. There is no rotational cycle to redistribute heat evenly. This creates a permanent imbalance. The day side remains extremely hot. The night side is comparatively cooler. The difference in temperature drives atmospheric circulation. High-energy regions generate pressure gradients. These gradients produce strong winds that transport material across the planet. Atoms, ions, and vaporized elements move from the day side to the night side and back again. This movement does not eliminate the temperature difference. It redistributes energy unevenly. The result is a system defined by flow rather than equilibrium. Energy enters continuously. Matter responds dynamically. Structure emerges from interaction, not stability. A second example reinforces this pattern. WASP-12b. This planet orbits even closer to its star, so close that gravitational forces begin to distort its shape. It is not perfectly spherical. It is stretched along the axis facing the star. This distortion has consequences. The outer layers of the planet extend toward the star. At a certain point, gravitational balance weakens. Material from the atmosphere begins to transfer outward. This creates a stream of gas moving away from the planet. In addition to thermal escape, there is tidal loss. The atmosphere is not only heated and expanded, it is being pulled. Observations show extended envelopes of gas surrounding this planet. These envelopes absorb specific wavelengths of light, indicating the presence of elements such as hydrogen and heavier species. The data suggests that the planet is losing mass over time. Not abruptly, but continuously. This introduces another layer of instability. The structure of the planet is not fixed. Its mass changes, its atmosphere evolves. Its long-term trajectory is not static. At this point, the distinction between planetary and stellar environments becomes less clear. Both involve high-energy radiation. Both involve ionized gases. Both involve radiative transfer as a dominant process. The difference is not in the behavior of matter. It is in the source of energy. Stars generate energy internally through nuclear fusion. Planets do not. But under extreme irradiation, a planet can exhibit external conditions similar to those found in stellar atmospheres. This places ultra-hot planets in an intermediate category. They are gravitationally planets, but thermodynamically they approach regimes associated with stars. This has implications for classification. Traditional definitions rely on formation and mass. A planet orbits a star and does not sustain fusion. A star generates energy through fusion. These definitions remain valid, but they do not fully describe physical behavior. Ultra-hot planets show that similar physical states can arise through different mechanisms. Internal fusion is not required to produce high-temperature atmospheric conditions. External radiation can achieve similar results. This suggests that classification systems are descriptive, not absolute. They group objects based on shared characteristics, but those characteristics can overlap. From a modeling perspective, this requires adjustment. Atmospheric models must include non-equilibrium chemistry, ionization processes, radiative transfer under extreme flux, coupled dynamics between temperature and composition. Standard equilibrium assumptions are not sufficient. There is also an observational implication. Spectral data from these planets must be interpreted with models that account for dissociation and recombination. Without this, measurements of composition and temperature can be misinterpreted. Over longer timescales, these processes influence planetary evolution. Atmospheric loss reduces mass. Chemical composition shifts as lighter elements escape. The remaining structure becomes denser and more enriched in heavier elements. This raises an open question. How stable are these planets over billions of years? Do they persist in this state, or do they gradually transform into different classes of objects? Current data provides partial answers, but not complete ones. What is clear is the following. Ultra-hot planets are not simply extreme versions of familiar worlds. They operate under different physical constraints. Their atmospheres do not settle. Their chemistry does not stabilize. Their structure is continuously shaped by energy input. This extends the known range of planetary behavior. It demonstrates that planetary environments can exist far beyond previously assumed limits. And it reinforces the central pattern established earlier. The laws of physics remain consistent.
But their outcomes depend on conditions. Change the conditions and the result changes completely. This leads directly to the next layer of complexity, because temperature alone does not define planetary structure. Rotation and the absence of it introduces a different form of imbalance, a condition where one side of a planet remains in constant radiation while the other remains in continuous darkness. And in that configuration, a new type of environment emerges. There are planets where time does not divide the surface into day and night. Instead, the division is fixed, permanent. On Earth, rotation creates a cycle. Light, then darkness. Heating, then cooling. This cycle distributes energy across the planet. It prevents extremes from becoming absolute. Even the hottest regions cool after sunset. Even the coldest regions eventually receive sunlight. Rotation is not just a measure of time. It is a stabilizing mechanism. But not all planets rotate freely. Some are gravitationally constrained. When a planet orbits very close to its star, tidal forces begin to act on its structure. Over time, these forces dissipate rotational energy. The planet slows. Eventually, its rotation period matches its orbital period. This is tidal locking. In this state, one side of the planet always faces the star. The same hemisphere receives continuous radiation. The opposite side remains in darkness. Not for hours, but indefinitely. This creates a fundamental asymmetry. The day side is exposed to constant energy input. The night side receives none. There is no cycle to redistribute heat through time. Only space remains. A well-known example is Proxima Centauri b. This planet orbits within the habitable zone of its star. Its distance allows for temperatures that could, under certain conditions, support liquid water. But its orbit is close enough that tidal locking is likely. This means that any potential habitability must exist within a system defined by permanent contrast. Another example is TRAPPIST-1e. Part of a compact multi-planet system, this world also orbits close to a relatively small star. Models suggest that it is tidally locked. Simulations of its atmosphere attempt to predict how energy might move across its surface. The key question is not whether these planets receive energy, it is how that energy is distributed. On the day side, continuous radiation leads to sustained heating. Temperatures rise until a balance is reached between incoming energy and outgoing radiation. But because the input is constant, the equilibrium temperature can be significantly higher than on a rotating planet at the same distance. On the night side, the situation is different. There is no direct radiation. Energy must arrive through transport. Without sufficient transport, temperatures can drop to extremely low levels. In extreme cases, atmospheric gases could condense or freeze. This creates a risk. If the atmosphere collapses on the night side, the planet loses its ability to redistribute heat entirely. The stability of a tidally locked planet depends on its atmosphere, specifically on its ability to move energy from the day side to the night side. Atmospheric circulation models address this problem. They simulate how gases respond to temperature gradients. A strong gradient produces strong winds. These winds transport heat from the day side toward the night side. If the atmosphere is dense enough and if circulation is efficient, heat can be redistributed before extreme cooling occurs. This prevents atmospheric collapse. It also reduces temperature differences between hemispheres. However, redistribution is not uniform. Energy is not spread evenly. Instead, it forms patterns. Jet streams, circulation cells, regions of rising and sinking air. These structures depend on planetary rotation rate, atmospheric composition, and surface conditions. Even with efficient circulation, a gradient remains. The day side stays warmer, the night side remains cooler. But between them, there is a transition region. a boundary. This region is known as the Terminator. It is the line that separates permanent day from permanent night. On a tidally locked planet, the Terminator is not moving. It is fixed in place. Conditions along this boundary are distinct. They are not as extreme as the day side. They are not as cold as the night side. Instead, they represent an intermediate environment, a zone where temperature may fall within a narrower range. This has led to a specific hypothesis. If liquid water is possible on a tidally locked planet, it is most likely to exist near the Terminator. Not across the entire surface, not concentrated at a single point, but distributed along a narrow band. This band is sometimes described as a potential region of stability. Not stable in the sense of unchanging, but stable relative to the extremes on either side. However, this stability is conditional. It depends on atmospheric thickness. It depends on heat transport efficiency. It depends on the presence of greenhouse gases that can retain energy. Without these factors, the Terminator may not provide sufficient moderation. Temperatures could still vary beyond the range required for liquid water. Another factor is stellar activity. Many tidally locked planets orbit small stars. These stars can produce strong flares and high levels of radiation. This introduces variability. Even in a system with fixed geometry, the energy input can fluctuate. This adds another layer of complexity. The environment is not only spatially asymmetric, it can also be temporally variable due to stellar behavior. From a physical perspective, tidally locked planets demonstrate that balance does not require symmetry. Energy does not need to be evenly distributed across time. It can be redistributed across space. But this redistribution is incomplete. The system maintains contrast, and that contrast defines its structure. This differs from Earth-like systems. On Earth, rotation smooths differences. On tidally locked planets, differences persist. They are fundamental to the environment. This leads to a broader implication. Habitability is not determined solely by distance from a star. It depends on how energy moves within a planetary system. A planet within the habitable zone may still be uninhabitable if energy cannot be redistributed. A planet outside traditional expectations may still maintain stable regions under the right conditions. This reframes the concept of environmental stability. Stability is not uniformity. It is the ability of a system to maintain conditions within a viable range, even if those conditions vary across regions. From a modeling standpoint, this requires multidimensional analysis. Temperature, pressure, atmospheric composition, and circulation must all be considered together. Simplified models based only on distance are not sufficient. Observationally, tidally locked planets present challenges. Their atmospheric signals are complex. Spectral measurements integrate information from multiple regions: dayside, nightside, and Terminator. Interpreting these signals requires separating overlapping contributions. Despite these challenges, the study of tidally locked worlds provides critical insight. It expands the range of known planetary environments. It shows that planetary systems can sustain long-term asymmetry. And it demonstrates that balance can emerge within that asymmetry. This continues the pattern established in the previous section. Extreme conditions do not eliminate structure, they redefine it. Temperature created the first level of complexity. Now, spatial imbalance adds another. And from this point, the analysis moves further. Because once energy distribution becomes uneven, and once atmospheric dynamics become dominant, the next question emerges.
how does matter behave under these conditions?
Not just in terms of temperature, but in terms of composition. And under extreme pressure and chemistry, a different class of planetary materials begins to appear. Temperature defines how matter behaves, but composition defines what matter becomes. On Earth, planetary materials follow a familiar pattern. Silicate rocks dominate the crust, iron forms the core, water exists as liquid, solid, and vapor under a narrow range of conditions. These materials are not arbitrary. They reflect the chemical composition of the early solar system, combined with pressure and temperature conditions during planetary formation. This creates an implicit assumption that rocky planets are primarily silicate-based, that metallic cores are iron-dominated, that water, if present, behaves within known phase boundaries. But this assumption depends on one condition, that the chemical environment of formation is similar. Outside the solar system, that condition does not always hold. A key factor is elemental abundance. Stars vary in composition. Some contain higher proportions of carbon relative to oxygen. Others show different distributions of heavy elements. Because planets form from the same material as their host stars, these differences propagate into planetary composition. This leads to alternative chemical pathways. Under certain conditions, carbon becomes a dominant structural element. Instead of forming silicate-rich planets, the system can produce carbon-rich bodies. A frequently discussed example is 55 Cancri e. This planet orbits close to its star and has a high density relative to its size. Early interpretations suggested that its interior might contain large amounts of carbon-based material, not in the form of organic compounds, but in crystalline structures formed under high pressure. At sufficient pressure, carbon atoms arrange into tightly bonded lattices. These structures are stable and dense. They differ fundamentally from silicate rock. If such materials dominate the interior, the planet's geology changes. Thermal conductivity, mechanical strength, and phase transitions follow different rules. The internal structure does not mirror Earth. It follows a different set of material properties. Pressure is the second defining factor. Inside planets, pressure increases with depth. On Earth, this produces transitions between different mineral phases. At higher pressures, atoms are forced closer together, creating denser arrangements. On more massive planets, these pressures become significantly higher. Materials that are stable on Earth may transform into entirely different phases. For example, water does not remain liquid or ice in the usual sense. Under extreme pressure, it forms high-density ice phases. These phases are solid, but structurally different from familiar ice. They can exist at temperatures where ice would normally melt. This principle applies to many materials. Silicates compress into denser forms. Metals change structure. Compounds reorganize at the atomic level. Another example is HD 149026b. This planet has an unusually large heavy element core relative to its total mass. Estimates suggest that a significant portion of the planet consists of elements heavier than hydrogen and helium. This affects its density. It also affects how the planet formed. A large core implies efficient accumulation of solid material during early stages. This challenges simplified models of gas giant formation, which often assumes smaller cores, followed by rapid gas accretion. In this case, the boundary between rocky and gaseous planets becomes less distinct. The planet contains both, but in proportions that differ from expectations. These examples illustrate a broader principle. Planetary composition is not fixed. It depends on initial conditions. elemental abundance, temperature during formation, pressure within the planet, and subsequent evolution. This leads to variability not only in structure, but in surface and atmospheric behavior. A carbon-rich interior may influence volcanic activity. A metal-rich composition affects magnetic field generation. High-pressure phases alter heat transport within the planet. Another important distinction is the ratio of carbon to oxygen. In oxygen-rich environments, silicon bonds with oxygen to form silicates. In carbon-rich environments, oxygen is less available for these reactions. Carbon instead forms stable compounds with itself or with metals. This changes the dominant materials. Silicate geology may be replaced by carbon-based structures. This is not a variation in detail, it is a shift in foundation. From a theoretical perspective, this expands the range of possible planetary types. Models must account for different chemical baselines. They cannot assume a single dominant composition. This also affects interpretation of observational data. Spectral signatures depend on atmospheric composition. If underlying chemistry differs, the expected signals change. Without accounting for this, conclusions about planetary structure may be incomplete. There is also an evolutionary aspect. Over time, planets undergo differentiation. Heavier elements sink toward the core, lighter materials rise. But the outcome depends on the initial composition. Different starting materials produce different internal layering. This influences long-term stability. Heat flow, tectonic activity, and magnetic field generation all depend on internal structure. A planet with a different composition will evolve differently. At this point, a pattern becomes clear. Temperature introduced variation in atmospheric behavior. Now, composition introduces variation in internal structure. These factors are not independent. They interact.
High temperature affects surface and atmospheric chemistry. Composition determines how materials respond to that temperature. Together, they define the physical state of the planet. This extends the concept of planetary diversity. Planets are not simply larger or smaller versions of Earth. They can differ in fundamental properties. The implication is direct. Earth-based intuition is limited. It reflects one combination of conditions. Other combinations produce different outcomes. This does not invalidate existing models. It expands them. Each new type of composition adds another dimension to planetary science, and it leads to the next layer of analysis. Because once composition varies and once temperature creates extreme conditions, the interaction between these factors produces complex atmospheric behavior, not just in chemistry, but in motion. And under these conditions, atmospheres no longer behave as steady systems. They become dynamic, high-energy environments shaped by continuous flow. Atmospheres do not only respond to temperature, they respond to imbalance. On Earth, atmospheric motion is driven by uneven heating. The equator receives more energy than the poles. Air rises, moves, cools, and returns. This creates circulation. It produces wind, weather, and climate. But the scale of this imbalance is limited. Rotation moderates it. Oceans absorb and redistribute energy. Time introduces cycles. On some exoplanets, these stabilizing factors are reduced or absent. What remains is imbalance at a much higher magnitude. A well-studied example is HD 189733b. This is a gas giant orbiting close to its star. Its atmosphere is exposed to intense radiation. It is also likely tidally locked. This creates a fixed pattern of energy input. The day side receives continuous radiation. The night side does not. The temperature difference between these regions is large. This difference generates pressure gradients.
In fluid systems, pressure gradients produce motion. The greater the gradient, the stronger the motion. On HD 189733b, this motion reaches extreme levels. Wind speeds are estimated to exceed several kilometers per second. These are not comparable to terrestrial winds. They are supersonic. At these speeds, atmospheric flow behaves differently. Shock fronts can form. Energy is dissipated not only through friction, but through compression and rapid changes in velocity. The flow becomes non-linear. Non-linear systems do not respond proportionally. Small changes in input can produce large changes in output. Patterns become complex. Predictability decreases. In such an atmosphere, circulation is not smooth. It is structured but unstable. Jets form and shift. Flows interact. Regions of turbulence develop. Radiation plays a central role. It does not only heat the atmosphere, it drives it. On the day side, energy input increases temperature and pressure. Air expands and rises. This creates a high-pressure region relative to cooler areas. The atmosphere responds by moving away from this region, toward the night side. As gas moves, it carries energy, but the transfer is incomplete. Cooling occurs during transit. When the gas reaches the night side, it releases energy into a colder environment. This process creates a continuous cycle: heating, expansion, transport, cooling, then return flow. However, because the system is tidally locked, this cycle does not rotate. It is anchored in space. The same regions experience the same conditions continuously. This leads to persistent flow patterns. Jet streams can become stable over long periods. But stability does not mean simplicity. The internal structure of these flows remains complex. Another feature emerges under these conditions: horizontal precipitation. On Earth, precipitation is driven by vertical motion. Water vapor rises, cools, condenses, and falls. The process is largely vertical. On ultra-hot planets, the situation changes. Condensation can occur in regions where temperature drops below the condensation point of certain materials. But strong horizontal winds dominate motion. As a result, condensed particles can be transported laterally. Instead of falling directly downward, they move across the atmosphere. This creates a form of horizontal precipitation. In the case of HD 189733b, observations suggest the presence of silicate particles. At high temperatures, silicates can exist in vapor form. As gas moves to cooler regions, these materials condense into small particles. Once formed, they are carried by high-speed winds. The motion is not vertical, it is lateral. Particles move across the atmosphere at high velocity. This is not analogous to rain on Earth. It is a different process, defined by temperature gradients and fluid motion, rather than gravity alone. Radiation-driven pressure gradients sustain this system. Energy input is continuous. There is no global equilibrium, only local interactions. At any given point, atmospheric conditions depend on multiple variables: temperature, pressure, velocity, composition. These variables interact. They influence each other. For example, temperature affects pressure. Pressure drives motion. Motion redistributes temperature. Composition affects how radiation is absorbed. This creates feedback loops. Feedback loops are a defining feature of non-linear systems. They can stabilize certain patterns or amplify disturbances. In extreme atmospheres, both effects can occur. Some regions maintain consistent flow, others shift unpredictably. From a modeling perspective, this presents a challenge. Simple equations are not sufficient. Full simulations require solving coupled systems of equations that describe fluid motion, energy transfer, and chemical processes. These models must account for radiative transfer, hydrodynamics, thermodynamics, chemical kinetics, all interacting simultaneously. Even with advanced models, uncertainty remains. Small variations in input parameters can produce different outcomes. This is not a limitation of theory, it is a property of the system. There is also an observational challenge. Measurements of these atmospheres are indirect. Spectroscopy provides information about composition and temperature, but it integrates signals over large regions. This makes it difficult to isolate specific processes. Instead, models are used to interpret the data. Observed spectra are compared to simulated spectra. The best match provides an estimate of atmospheric conditions. Despite these limitations, several conclusions are consistent. Atmospheric motion on these planets is extreme. Radiation is the dominant driver. Equilibrium is not achieved. This extends the concept of weather. On Earth, weather is variable but bounded. It fluctuates within a range defined by planetary conditions. On these exoplanets, the range itself is expanded. Wind speeds exceed terrestrial limits. Temperature gradients are larger. Material behavior differs. This does not mean the system is chaotic in the sense of random. It follows physical laws, but the outcomes are more complex. At this point, a broader pattern becomes visible. Temperature created extreme conditions. Tidal locking introduced spatial imbalance. Atmospheric dynamics respond with high-energy motion. Each layer builds on the previous one. Each adds complexity. And this leads to the next stage of analysis. Because atmospheric motion does not exist in isolation. It is connected to orbital behavior. The shape of an orbit, its orientation, and its interaction with other bodies all influence how energy enters the system. When those orbits become unstable or misaligned, a new level of complexity emerges. Not in the atmosphere, but in the structure of the system itself. Orbits are often assumed to be stable, predictable, ordered, repeating. This assumption comes from observation. Within the solar system, most planets orbit in the same direction as the Sun's rotation. Their paths are nearly aligned. Their motion appears coordinated. This creates a sense of structure. But this structure is not universal. Beyond the solar system, orbital configurations vary. Some planets follow paths that do not align with their star's rotation. Others move in the opposite direction entirely. A clear example is WASP 17b. This planet orbits its star in a retrograde direction. Its motion is opposite to the rotation of the star itself. This is not a minor deviation. It represents a fundamental difference in system architecture. In standard formation models, planets emerge from a rotating disk of gas and dust. This disk has a consistent direction of motion. As planets form, they inherit that direction. Retrograde motion cannot be explained by this process alone. It requires disruption. One possible mechanism is gravitational scattering. In systems with multiple large bodies, gravitational interactions can alter orbits. When planets pass close to each other, energy and momentum are exchanged. This can change orbital paths. Inclinations increase, eccentricities grow, directions can reverse. These interactions are not gradual. They can occur over relatively short timescales. A stable configuration becomes unstable. Another mechanism involves external influence. A nearby star or a distant companion can exert gravitational forces on a planetary system. Over long periods, these forces can alter orbital orientation. This process is often described through dynamical effects that change the angle of an orbit relative to the star's rotation. The result is misalignment. In extreme cases, retrograde motion. A second example illustrates this complexity, the Kepler-56 system. In this system, multiple planets orbit a star whose rotational axis is tilted relative to their orbital plane. This means the planets do not orbit along the star's equator. Their motion is inclined. The system lacks alignment. This is significant. It shows that even when planets share the same direction of motion, the overall structure can still be misaligned. These observations challenge the assumption that planetary systems settle into simple configurations. Instead, they reveal that systems can retain the imprint of past interactions. Gravitational scattering is one source of this imprint. During early formation, systems may contain multiple large bodies in close proximity. Their interactions can be intense. Some planets may be pushed inward, others outward. Some may be ejected entirely. Orbital resonance adds another layer. When planets orbit in ratios of whole numbers, their gravitational influence becomes periodic. This can stabilize motion, but it can also destabilize it. If resonance conditions change, the system can shift. Small deviations can grow over time. Resonance breakdown occurs when these periodic interactions no longer maintain balance. Orbits can become more eccentric. Crossing paths may develop. This increases the likelihood of close encounters, which leads back to scattering. From a modeling perspective, these systems are described using n-body simulations. Each body influences every other body. The equations governing motion are well understood, but the outcomes are sensitive to initial conditions. Small differences in starting positions or velocities can produce very different long-term results. This is a property of chaotic systems. Chaos does not mean randomness, it means sensitivity. Given enough time, predicting exact positions becomes difficult, but statistical behavior can still be analyzed. Long-term instability modeling attempts to understand these patterns. It does not predict exact trajectories, it estimates probabilities. For example, what fraction of systems will remain stable over billions of years? What fraction will experience scattering events? How often do retrograde orbits emerge? Current models suggest that instability is common during early stages. Systems may begin in compact configurations. Interactions then redistribute mass and momentum. Some systems settle into stable arrangements, others do not. This leads to a broader conclusion. Planetary systems are not static, they evolve. Their current configuration is the result of past interactions, not an initial design. Retrograde motion is one outcome of this evolution. It is not an anomaly. It is a possible state within a range of outcomes. This reframes how orbits are interpreted. Instead of viewing alignment as the default, it becomes one case among many. Misalignment, inclination, and retrograde motion are part of the same spectrum. They differ in degree, not in kind. This perspective also affects how stability is defined. A system may appear stable at present, but that does not guarantee long-term stability. Gravitational interactions continue. External influences persist. Over time, configurations can change. There is also a connection to planetary survival. Not all planets remain in their original systems. When instability becomes strong enough, a planet can be ejected. Its velocity increases beyond the escape velocity of the star. it leaves the system entirely. This is not a rare outcome in simulations. It is a natural consequence of strong gravitational interactions. At this point, the concept of a planet changes again. It is no longer defined by its orbit around a star. It becomes an isolated object, moving through space without a central source of energy. This leads directly to the next stage of analysis. Because once planets are no longer bound to stars, their environment changes completely. No radiation from a host star, no stable orbital path, only internal processes remain. And under those conditions, a different type of planetary existence emerges. One defined not by proximity to a star, but by isolation. Not all planets remain bound to a star. Some are removed. In stable systems, planets orbit a central source of gravity. Energy comes from that star. Temperature is defined by distance. This creates structure. But when orbital stability breaks down, that structure can collapse. Gravitational interactions can accelerate a planet beyond escape velocity. Once that threshold is crossed, the planet no longer returns. It becomes unbound. These objects are known as rogue planets. They do not orbit stars. They move through space independently. One example is OGLE-2016-BLG-1928. This object has a mass comparable to Earth. It was detected through gravitational microlensing. Microlensing occurs when a massive object passes between an observer and a distant star. The gravity of the foreground object bends the light of the background star. This produces a temporary increase in brightness. The duration and shape of this signal reveal the mass of the intervening object. In this case, the signal was short. This indicated a low-mass object.
No host star was detected. The most consistent interpretation is that the object is a free-floating planet. Another example is PSOJ 318.5-22. This object is more massive. It emits detectable infrared radiation. That radiation does not come from a nearby star. It comes from the object itself. When planets form, they retain heat. Gravitational compression during formation generates thermal energy. Radioactive decay within the interior can also contribute. In systems with stars, this internal heat is often overshadowed by stellar radiation. But for rogue planets, internal heat becomes the primary energy source. Over time, this heat dissipates, but the rate of cooling depends on size, composition, and structure. Larger planets retain heat longer. This creates an unexpected possibility. Even without a star, a planet may maintain internal temperatures sufficient to support liquid layers beneath the surface. This leads to the subsurface ocean hypothesis. If a planet contains water, and if internal heat is sufficient, ice at the surface can insulate deeper layers. Beneath that ice, liquid water may persist. This does not require sunlight. It requires pressure and heat. Pressure increases with depth. This raises the melting point of ice under certain conditions. At the same time, internal heat provides energy. Together, these factors can create a stable liquid layer beneath a frozen exterior. This type of structure is not purely theoretical. Similar conditions are considered for icy bodies within the solar system. But on rogue planets, the scale can be larger. The absence of a star changes the external environment. Surface temperatures are extremely low. There is no day-night cycle, no seasonal variation. The surface becomes static, but the interior remains active. This creates a separation. The exterior is defined by cold and isolation. The interior is defined by retained energy and potential activity. From a physical perspective, this is a different type of planetary system. Energy does not enter from outside. It originates from within. This changes how habitability is considered. Traditional models rely on stellar energy. Distance from a star defines the habitable zone. Rogue planets do not fit this framework. They exist outside any stellar zone. Yet, if subsurface oceans are possible, then liquid environments can exist without external radiation. This expands the definition of habitable conditions. Energy can come from internal processes, not only from stars. There are limitations. Internal heat decreases over time. Without replenishment, the system cools. Eventually, liquid layers may freeze. The duration of potential habitability depends on planetary mass and composition. Larger planets remain active longer. Smaller planets cool more quickly. Another factor is insulation. A thick outer layer can slow heat loss. This extends the lifetime of internal activity. From an observational standpoint, rogue planets are difficult to detect. They do not emit strong visible light. They do not transit stars. Microlensing provides one method. Infrared surveys provide another, but both have limitations. This suggests that the number of rogue planets may be larger than currently observed. Detection bias favors planets near stars. Free-floating objects are less visible. Statistical models estimate that rogue planets could be common, possibly as numerous as stars in some regions. If this is correct, then planetary systems do not define the full population of planets. There exists a separate population, unbound, distributed across interstellar space. This leads to a broader implication. Planets are not defined solely by their relationship to stars. They can exist independently. Their formation may begin within systems, but their final state does not require a central object. This challenges the traditional structure of planetary science. It shifts focus from systems to objects. Each planet must be understood in terms of its own properties, not only its position within a system. At this stage, a pattern continues to develop. Instability produces new configurations. Some planets remain in altered orbits. Others are removed entirely. But removal does not end their evolution. It changes the conditions under which that evolution continues. This leads directly to the next question. If planets can exist without stars, and if internal processes can sustain liquid environments, then what forms of stability are possible? Not in isolation alone, but in systems where a single material dominates. And under those conditions, a different type of planetary structure emerges. One defined not by rock or gas, but by a continuous, global ocean. Not all planets are defined by land. Some are defined by water. On Earth, water covers most of the surface, but it does not dominate the structure. Continents exist. Geological cycles operate through interaction between rock, ocean, and atmosphere. This interaction is essential. It regulates temperature, it cycles nutrients, it supports long-term stability. Ocean worlds differ at a fundamental level. Water is not a surface feature, it is the primary component. A candidate example is Kepler 22b. This planet orbits within the habitable zone of its star. Its size suggests it may contain a significant amount of water. Another example is TOI 1452b. Observations indicate that a large fraction of its mass could be composed of water or water-related materials. These planets are not simply Earth with deeper oceans. Their internal structure is different. At the surface, a global ocean may extend across the entire planet. No continents, no exposed rock. Below this ocean, pressure increases rapidly with depth. At sufficient pressure, water transitions into high-density ice phases. These are not familiar forms of ice. They do not float. They are denser than liquid water. They form solid layers beneath the ocean. This creates a layered structure: atmosphere, liquid ocean, high-pressure ice, rocky interior. The presence of high-pressure ice creates a barrier. It separates the ocean from the rocky core. On Earth, interaction between water and rock is essential. Minerals dissolve into the ocean. Hydrothermal systems transfer heat and nutrients. These processes support chemical cycles. On ocean worlds, this interaction may be limited or absent. The ice layer prevents direct between liquid water and the rocky interior. This has implications for chemistry. Without continuous input of minerals, the ocean may lack essential elements for complex processes. Nutrient cycling becomes constrained. There is no equivalent of plate tectonics, no continental erosion, no large-scale recycling of material between surface and interior. This does not prevent all chemical activity. Dissolved elements may still exist. Internal heat may create localized manicle of activity beneath the ice. But the overall system is less dynamic. From a biological perspective, this matters. Complex systems require gradients, energy gradients, chemical gradients. These gradients drive processes. On Earth, such gradients are sustained by interaction between different layers. On ocean worlds, the separation between layers reduces these interactions. This does not eliminate the possibility of life, but it changes its simple forms of life may exist under limited conditions. But the development of complexity depends on sustained chemical cycling. This introduces a distinction. Habitability is not binary, it is a spectrum. A planet may contain liquid water, but that alone does not guarantee a complex environment. Ocean worlds demonstrate this clearly. They meet one condition, liquid water, but other conditions may not be satisfied. Temperature also plays a role. If the planet is within the habitable zone, surface conditions may allow stable liquid water. If it is closer to its star, the ocean may become unstable. If it is further away, freezing may dominate. Internal heat can extend stability, but only within limits. Pressure remains constant. Depth defines structure. The deeper the ocean, the thicker the high-pressure ice layer. This increases separation from the core, further reducing interaction. From a modeling perspective, ocean worlds require different assumptions. Standard Earth-based models include atmosphere-ocean interaction, ocean crust interaction, crust-mantle cycling. Ocean worlds simplify this structure, but that simplicity introduces constraints. Fewer interactions mean fewer feedback mechanisms. Fewer feedback mechanisms reduce system adaptability. This affects long-term stability. A system with limited feedback is less capable of maintaining balanced conditions over time. There is also an observational limitation. Detecting oceans directly is difficult. Measurements rely on density, radius, and atmospheric. From these, scientists infer composition. But uncertainty remains. Despite this, the existence of water-rich planets is supported by multiple observations. They appear to be common in certain size ranges. This suggests that ocean worlds are not rare exceptions. They are part of the broader distribution of planetary types.
This expands the definition of planetary environments. Not all habitable candidates resemble Earth. Some are fundamentally different. At this stage, a pattern continues. Planets vary in temperature, they vary in composition, they vary in structure. Now, they vary in dominant material. Water, in this case, defines the system, not as a component, but as the primary medium. This leads to a broader implication. The presence of a familiar substance does not guarantee familiar conditions. Water exists, but its behavior depends on pressure, temperature, and context. On Earth, it supports complex systems. On ocean worlds, it may remain isolated. This distinction is important. It separates appearance from function, and it leads directly to the next level of analysis. Because planetary structure is not only defined by current conditions, it is shaped by time, by formation history, by chemical evolution, by changes across billions of years. And when these factors are considered, planets are no longer static objects. They become stages within a longer process, one that extends across the lifetime of the universe itself. Planets are not only shaped by space, they are shaped by time. Every planet exists within a timeline, a sequence that begins long before the planet forms and continues long after its structure stabilizes. To understand the planet fully,
It is not enough to describe its current state. Its origin must be considered. A key example is PSRB 1620-26b. This planet is estimated to be more than 12 billion years old. It formed when the universe was still relatively young. At that time, the chemical composition of the universe was different. Only the lightest elements were abundant. Hydrogen and helium dominated. Heavier elements were less common. These heavier elements, carbon, oxygen, silicon, iron, are produced inside stars. They are released when stars evolve and disperse material into space. This process takes time. Early in the universe, fewer generations of stars had existed. This meant fewer heavy elements were available. Planet formation depends on these elements. Rocky planets require silicon and iron. Water requires oxygen. Complex chemistry requires carbon. In environments with low heavy element abundance, planet formation proceeds differently. The existence of PSRB 1620-26b shows that planets can form even under these conditions. But the process is constrained. The types of planets that form may differ from those in later epochs. A second example provides contrast. The Kepler 444 system. This system is also very old. Its planets formed early in the history of the galaxy. Despite their age, the system contains multiple small, rocky planets. This indicates that even with limited heavy elements, rocky planet formation was possible. However, the composition and structure of these planets may differ from younger systems. Subtle differences in elemental ratios can affect mineral composition. This introduces the concept of metallicity. In astrophysics, metallicity refers to the abundance of elements heavier than hydrogen and helium. Higher metallicity means more building material for planets. Lower metallicity means fewer heavy elements. Metallicity influences planet formation efficiency. Systems with higher metallicity tend to form more massive planets. Gas giants are more common in such systems. In lower metallicity environments, planet formation may favor smaller bodies. This creates a variation across time. As the universe ages, metallicity increases. Each generation of stars enriches the interstellar medium. This process is known as cosmic chemical evolution. It is cumulative. Material from previous stars becomes the raw material for new systems. Over billions of years, this leads to increasing diversity. More elements become available. More complex compounds can form. This affects not only planet formation, but also planetary composition. Later generation planets have access to a wider range of elements. This allows for more varied structures, more complex chemistry. Early generation planets are more limited, but they still exist. They represent earlier stages in the chemical history of the universe. From a temporal perspective, planets can be grouped into generations. First-generation planets form in low metallicity environments. Second-generation planets form after some enrichment. Later generations form in chemically rich environments. Each group has different characteristics, not because the laws of physics change, but because the available mawad change. This introduces a time dimension to planetary diversity. Previously, variation was described in terms of temperature, composition, orbital behavior. Now, variation includes age. Two planets with similar size and position may differ significantly if they formed at different times. This also affects long-term evolution. Over billions of years, planets cool. Internal heat decreases. Geological activity slows. Atmospheres evolve. They can be lost through escape or altered through chemical reactions. External events also play a role. Stellar evolution changes radiation levels. Nearby events, such as supernovae, can affect planetary systems. All of these factors contribute to planetary evolution. A planet is not fixed.
It changes, gradually, continuously. This change can move a planet through different states, from active to inactive, from warm to cold, from chemically dynamic to stable. In some cases, conditions that were once favorable may no longer exist. In others, new conditions may emerge. This reinforces a key idea. Planetary properties are not permanent. They are temporary states within a longer process. From an observational standpoint, this introduces complexity. When a planet is observed, only its current state is visible. Its past must be inferred. This requires models. Models that connect current observations to possible formation histories. These models include stellar evolution, disk chemistry, planetary migration, atmospheric loss. Each factor contributes uncertainty. Multiple histories can produce similar outcomes. This limits precision, but it does not prevent understanding. Instead, it shifts focus from exact histories to probable scenarios. At a larger scale, this perspective connects planetary science to cosmology. Planets are not isolated objects. They are part of a sequence that begins with the formation of elements in stars. This sequence continues through stellar evolution, material dispersal, disk formation, planet formation, and then through planetary evolution itself. Each stage depends on the previous one. This creates continuity, from the earliest stars to the present structure of planetary systems. At this point, the scale expands further. Variation is no longer limited to space. It extends across time. Different regions of the universe may contain planets at different stages of this timeline. Some systems are young, others are ancient. This creates a distribution of planetary types not only in space, but across history. This leads to a final constraint. Observation is limited. We observe planets at specific moments. We do not observe their full evolution. This introduces uncertainty. and that uncertainty defines the boundary of current knowledge. Because no matter how detailed the analysis becomes, it remains based on incomplete information. And that limitation leads directly to the next stage. Not a new type of planet, but a constraint on all observations. The question is no longer only what exists, but also what remains unseen, and how much of the universe is still beyond detection. Observation defines knowledge, but observation is not neutral. Every measurement depends on method, and every method introduces bias. In planetary science, this bias is not a flaw, it is a constraint. We do not observe all planets equally. We observe the ones that are easiest to detect. This creates a filtered view of reality. One of the most influential instruments in this field is the Kepler Space Telescope. Its primary method was transit detection. A transit occurs when a planet passes in front of its star from the observer's perspective. This causes a small decrease in the star's brightness. The depth of that decrease reveals the size of the planet, the timing reveals its orbital period. This method is effective, but it has limitations. First, alignment is required. The planet's orbit must be oriented so that it crosses the line of sight. If the orbit is tilted, no transit is observed. This excludes a large number of planets. They exist, but they remain undetected by this method. Second, transit detection favors short orbital periods. Planets that orbit close to their stars pass in front of them more frequently. This provides more data points. It increases detection confidence. Planets with longer orbital periods transit less often. Observing them requires longer monitoring. In many cases, the data is insufficient. This creates a bias. Close-in planets are overrepresented. Distant planets are underrepresented. Third, signal strength matters. Larger planets block more light. They produce clearer signals. Smaller planets produce weaker signals. They are harder to detect. This leads to another bias. Large planets are easier to observe. Small planets are more difficult. Together, these factors shape the observed population. The result is not a complete sample. It is a selection. This must be considered when interpreting data. Another major instrument is the James Webb Space Telescope. Its capabilities differ. It does not focus primarily on detection. It focuses on characterization. Specifically, it analyzes planetary atmospheres. When a planet transits its star, a small fraction of starlight passes through its atmosphere. Different elements absorb different wavelengths. By measuring these absorption patterns, scientists infer atmospheric composition. This allows detection of molecules such as water vapor, carbon dioxide, methane. However, this method also has limitations. It requires strong signals. Atmospheric signatures are subtle. They depend on the thickness and composition of the atmosphere. Planets with thin atmospheres produce weak signals. Detection becomes uncertain. Distance is another constraint. More distant systems produce weaker signals. Signal-to-noise ratio decreases. Time is also a factor. Detailed observations require long exposure times. Only a limited number of targets can be studied in depth. This introduces another form of selection. Only certain planets are characterized. Others remain unexamined. Beyond instrument limitations, there are theoretical constraints. Data interpretation depends on models. Spectral signatures must be matched to atmospheric compositions.
but multiple compositions can produce similar signals. This creates degeneracy. Different scenarios can explain the same observation. Resolving this requires additional data, or assumptions. Both introduce uncertainty. There is also a broader issue: undetected populations. Planets that do not transit. Planets too small to detect. Planets too distant. These objects are not included in current catalogues, but they exist. Statistical methods attempt to account for this. They estimate the number of unseen planets based on observed distributions. These estimates suggest that planets are extremely common, but exact numbers remain uncertain. This leads to a key realization. What is known is only a fraction of what exists. The observed population is shaped by detection methods. It does not represent the full diversity of planetary systems. This introduces humility. Scientific conclusions must account for incomplete data. Patterns may shift as new observations are made. Technological advancement changes the boundary. Future instruments will detect smaller planets, more distant planets, planets in different environments. Each improvement expands the dataset, but the boundary never disappears. It moves. There will always be limits. From a methodological perspective, this requires caution. Conclusions must be framed within the context of detection bias. Trends must be interpreted statistically, not absolutely. This also affects theoretical models. Models must remain flexible. They must adapt to new data. Rigid assumptions are not sustainable. This connects back to earlier sections. Extreme planets were discovered because methods improved. Hot Jupiters were found first, not because they are most common, but because they are easiest to detect. As detection methods expanded, new types of planets were identified. This suggests that current classifications are provisional. They reflect what can be observed, not necessarily what is most typical. At this point, a broader pattern becomes clear. Knowledge expands through observation, but observation is constrained. This creates a balance: confidence in what is known, uncertainty about what is not. This balance defines the current state of planetary science. It is not incomplete in the sense of lacking structure. It is incomplete in the sense of ongoing discovery. And this leads directly to the next stage. Because once the limits of observation are acknowledged, the focus shifts from describing individual systems to understanding their broader meaning. Not only what planets are, but what they imply about habitability, about life, and about the position of Earth within a much larger system.